Assalamualaikum warahmatullahi ta'ala wabarakatuh. Bismillahirrahmanirrahim. So example 6 is also related to unsteady flow, but compared to example 5 that we looked at in the last sections, here we will have flow at inlet as well as flow at exits. So the question says that the open tank shown in this diagram here has a constant inflow discharge of 0.1 meter cube per second. So there is a inlet flow here, and the flow rate is equal to 0.1 meter cube per second. A 10 centimeter diameter drain provide a variable outflow V out is equal to root 2 GH. So there is an outflow here through this 10 centimeter diameter drain, and the velocity here is equal to root 2 GH. The question asks us to determine the equilibrium height, H equilibrium, of the liquid in the tank. So first of all, let's draw a schematic diagram of the problem. So now we have the tank. Let's say the cross-sectional area of the tank is equal to AT, and then the height of the water inside the tank is equal to H. The volume flow rate at inlet is given as 0.1 meter cube per second, and then we have a drain at the bottom here, and then the outlet velocity is equal to root 2 GH, where H is the height of the water at that particular instance. And then let's say the cross-sectional area of the drain is equal to A naught, and the diameter of the drain is given as 10 centimeter or 0.1 meter. So the whole of the tank is our control volume. So if we apply the mass conservation equations, the general mass conservation equation says that the rate of change of mass of the control volume is equal to mass flow rate in minus mass flow rate out. In this case, we are using water. Water is an incompressible fluid, so the flow is incompressible flow. So we can change the mass flow rate to volume flow rate. So we have dVc by dt is equal to dot in minus discharge for the volume flow rate out. So now if you consider each one of these, dVc by dt, this is equal to d by dt. So the volume is equal to AT multiplied by H, right? And then the volume flow rate in, that is equal to, we only have one inlet here, is equal to V dot 1, and that is given as 0.1 meter cube per second, right? Whereas the volume flow rate out, or discharge out, is equal to velocity out multiplied by V out, and equal to A out root 2 GH, right? Okay, so now if we substitute all this into this equation, so we can write d by dt ATH, and this must be equal to V dot 1 minus A naught root 2 GH, right? So now at equilibrium, what will happen is that d by dt ATH will tend to 0, or in a limit will be equal to 0, whereby at that point H will tend to equilibrium height. So if I were to plot graph of H against time, and let's say this is the H equal to H equilibrium, the height of the water will asymptotically approaching the value of H equivalent. So depending on the initial value of H, the graph can either be like this, where this is the Hi, or the graph can also be, let's say, like this, where this is Hi, right? So it will follow this graph, if this value here initially positive. So that means that if v dot 1 is actually bigger than a naught root 2g hi, so it will be like this. Or if v dot 1 is actually less than a naught root 2g hi, so this value here will be negative. So the gradient here will be negative, so it will be like this. At equilibrium, 1 minus a naught root 2g h equilibrium will be equal to 0. So we can rearrange this. So we have a naught root 2g h eq will be equal to 1. So this will give us h eq and is equal to 1 over a naught squared multiplied by 1 over 2g. So substituting the value, so we have 0.1, then the exit area is by 0.1 squared over 4, and everything is squared, multiplied by 1 over 2, 9.81. This will give us H equilibrium is equal to 8.26 meter. Okay, so the equilibrium height is 8.26 meter.